Number 10, we want to find the points of intersection between the two graphs, the green and the blue. Well, if you want to find a point of intersection, you would simply set the two equations equal to each other. So I will do that now. Subtracting 1 from both sides is going to give me negative 2 cos theta equals 0. Dividing that by negative 2 will make cosine of theta equals 0. Therefore, theta either has to be pi over 2 or 3 pi over 2. If theta is pi over 2, we're going to be up here where 90 degrees is, and that's obviously the point 0, 1, which is one of our 3 answers. If theta is 3 pi over 2, we're going to be right here at 0, negative 1, which again is another one of the 3 correct answers. But the third answer, and clearly it crosses in a third space, you can see it there, but the algebra's done. It's not giving us the third answer, which is clearly negative 1, 0. But why will this third point, this large red point, not show up anywhere in the algebra? And the reason it doesn't show up is because green and blue don't get there at the same time. In fact, when I was in high school and we were learning all the planets, you remember Pluto? Used to be a planet, then got kicked out of the solar system. I don't even know if it's back or not. Neptune was the farthest planet from the sun for a brief period of time. Here's the sun, and then Neptune's orbit was fairly normal. And Pluto had a crazy elliptical orbit that went a little weird. It was normally the farthest planet, but just for a brief period of time, it came inside of Neptune and then went way out and around. This was the time I was in high school, and I think briefly in college as well. Pluto was not the farthest planet out. So what I'm trying to tell you is the 2 planets' orbits cross each other twice. But thank goodness Neptune and Pluto have never collided with each other because they weren't there at the same time. And for the answers to show up in the algebraic steps, the graphs have to hit the same point at the same time, which is why this negative 1, 0 just has to be done by inspection. You can't get it from an equation. Both of the equations do go through that point, negative 1, 0, just at different angles. So those are your points of intersection. Okay, for number 11, again, we want to find the points of intersection. You can see that there's 3 of them, and one answer is definitely 0, 0. They both go through the origin. I made a close-up so you can see that red dot. The 0, 0 will not show up with the algebra for the same reason in the last problem. The curves don't hit 0, 0 at the same theta angle. They do hit each other at the blue dots. And the blue dots come from the blue algebraic work down the left-hand side. You can see I set them equal to each other. I solved. I got theta equals pi over 3, or 60 degrees, and 5 pi over 3, which is going to be a quadrant 4 angle, and that's going to be 300 degrees. The pi over 3 and 5 pi over 3, you can see I already have in my answer. How do I know that the radius is 1/2? Because again, it's r comma theta. We're in polar coordinates. Well, just take either one of these, really, and just plug them into either place. I think it'd be a little easier if I plugged it into the second one. And the cosine of theta, cosine of pi over 3, or the cosine of 5 pi over 3, either way, they're going to be 1/2. Since one is in quadrant 1 and one is in quadrant 4, cosine's positive in both of those quadrants anyway, so positive 1/2 for the radius on each one. And then, of course, 0, 0. So that's number 11. Number 12 wants us to find the area of the common interior of those two. So you have to be inside the green and inside the blue at the same time. Well, first of all, I set them equal to each other to see where they would intersect. I'll save you the algebra on that just because the slides are only so big here. But they do cross each other at 2 pi over 3 and 4 pi over 3. I threw a couple red lines in there just to kind of help us visualize this a little bit better. Okay, again, let's start with the area formula for a polar region. We know that that's going to be 1/2 the integral of radius squared d theta. This problem is really going to be two separate cases. We're going to have the blue function leading off, and then the green function is going to take over. Also, I'm going to use symmetry to my advantage. I'm just simply going to take the area of the top half, or the top blue part, and then double the entire thing. I'm going to put a giant 2 in front of the whole proceedings here, which will act to cancel out both of the 1/2 through the distributive property. Therefore, I don't have to deal with any of that. So I'm really only going to be finding the top part of this, and then just doubling my answer later. Okay, here's what happens. We start out with the blue curve, which is the -6 cos theta. And then we end up with the green curve, which is the 2 minus 2 cos theta. Okay, using my really unusual idea of shooting a water gun out, let's say that we start at the pole again, and I start shooting straight to the right. Well, immediately I'm going to hit the blue, and even when I'm shooting straight up at 90 degrees, I'm hitting the people in the blue line at extremely close range. That's got to hurt. As I get into quadrant 2, you can see I'm fanning out a little bit more, but the people in the blue line are basically getting abused. And so they're taking the hit all the way from 0 to 2 pi over 3. The 0 and the 2 pi over 3 will become the limits of the first integral. After I cross the red line, you can see that the water gun is not hitting the people in the blue line anymore. It's almost like the folks in the green curve are stepping up and being like, you know what, we got this. We'll take the shots for you. And so they get hit all the way from 2 pi over 3 to pi. And then the story ends. Now, like I've already said, I've already doubled the whole thing out in front, so that's going to cover the bottom part that I didn't do yet. So at this point, just to save a little time and aggravation, we're not going to go ahead and FOIL both of those out and start plugging things in. We're going to use the calculator. The portion that you see in blue is obviously the smaller of the two. That's going to come out to 1.63055. And the portion in green, which is obviously the larger part of this, is going to be 14.07741. Add these together, round to 3 places, and you get the final answer of 15.708 square units. By the way, if you were to do all the work, you would find out that 15.708 is actually an exact answer of 5 pi, just rounded off a bit. So 5 pi is the pure answer, but that's a lot of extra work to come up with that. That's not something College Board's going to expect you to do. All right, finally, the last one, number 13. It says, find the area of the given region inside the blue circle, but outside the green cardioid. Well, these shapes are going to cross each other right up here at pi over 2, will be the theta. And if you can't really see that that's pi over 2, just take the two equations, the blue and the green, and set them equal to each other and solve, and theta will be pi over 2. So I'm going to integrate from 0, which of course is right along the x-axis, to pi over 2. What that'll do, I'm going to start with the blue. If I start with the blue, I'm going to get this region right here, which is actually just a quarter circle, as it turns out. And then I'm going to come back by subtracting the green from 0 to pi over 2. That'll subtract that white region away. So it's going to be blue minus green from 0 to pi over 2. Now again, I should mention that I've only gone from 0 to pi over 2, which is really only the top half of the yellow region. but I'm going to go ahead and double it in front. This red 2 is from symmetry. And again, with distributive property, it's going to cancel out the 1/2. So those will be out of our way. So now it's just simply going to be integrating the 1 and the 1 minus cos theta squared. And that should be pretty easy. In fact, since this is the last one and the math's not quite as cumbersome, I'm going to get an exact answer on this one. So let's start with the blue. The integral of 1 is just theta. So that's theta. And we're going to take that from 0 to pi over 2. Minus, and then 1 minus cos of theta squared. I'm going to write that up here. And when I integrate this term by term, I'm going to get theta minus 2 sine of theta. And here comes the tricky part. Cosine squared, remember that's the memorized formula. So it's plus 1/2 theta. Always, always, always. Cos is the plus. This is always a sine, but it's a double angle. So instead of theta, it's 2 theta. All right, we're going to take this to a blank page so we have some room to knock it out. Putting the pi over 2 in and putting the 0 in is simply going to give us pi over 2 minus 0, or pi over 2. Bring down the black minus sign. Here it comes. And let's keep some green parentheses in the mix. Pi over 2 is going to go first. Obviously, that'll be pi over 2. The sine of pi over 2, sine of 90 is 1, so that's going to be minus 2. Half of pi over 2 is pi over 4. That's positive. And this is going to end up being sine of pi, which is 0. And I think it's pretty easy to see if you plug the 0 in everywhere, you're going to get a whole bunch of zeros. You're going to get a whole bunch of nothing. So I'm not going to bother with that. We do have to do distributive property here. The pi over 2 will knock the negative pi over 2 out, but we are going to get a couple other things happening. Negative times negative will be positive 2 minus pi over 4. And that is the exact answer. If you want a decimal approximation, it's 1.214 or 1.215. Because it comes out to 1.2146. But this thing right here is definitely the best answer. It's the exact answer. All right. Well, guess what we just did? We made it through BC Calculus. That's the end of the year. I hope you guys enjoyed the class. And if you have any questions, just let me know. But we did it. Congratulations.